Welcome to Energy Radio. On this episode, we are going to get deep into the bug dust, so to speak, and we're going to talk to somebody who I've gotten to know quite well and think highly of on a bunch of different levels. I think in some ways, the highest level as a fellow business owner, and what that means to serve customers, and we're aligned and we work together a lot on stuff. And we've made an exception on this podcast because usually we try to have owners. But we've got, I would say, a business owner, obviously, not a project owner, but I think the next best thing. So Dave Ellis is my guest today on the podcast. Dave, welcome.
Well, thank you, Matt. Terrific to be here. Really appreciate the opportunity to speak to you and your listeners.
Yeah, no, that's great. And I was trying to remember this morning how you and I have met. Like that, and we've done a bunch of stuff together. We run into each other all the time. But that part of the story is blank for me. Do you remember how we met?
I'm trying to remember that as you bring that up. I think I'm assuming it must have been at one of the Canadian Biogas Association conferences. I'm assuming that must have been it. Must have been, yeah. When I started going there, maybe 2015 kind of time frame.
Okay.
That's when I started to meet a whole lot of people in this space coming from my background in more wastewater and that other industry before bridging into this.
Yeah, okay, cool. Yeah, and that's probably what it is. I can't specifically remember it, but I'm sure if we ask Natalie, she'll remember.
She remembers a lot.
She does, yeah. So speaking of your background, why don't we start there? Kind of give the listeners... Because as I said to you before, like I think your background is so rich in terms of kind of, I think the kids would call you an OG, like, you know, is that right, Tricia? Yes. Yeah. Okay. You know, that you have this background, whereas folks like me who kind of came out of school and biogas was already kind of becoming cool. You were kind of doing it before it was cool. So at least that's my interpretation. So give the listeners your background and how you come to this today.
You're very kind. Yeah. So I would say that, this is an overnight success that's been 40 or 50 years in the making, really. Yeah. And to that, I'm just lucky and very grateful. My background is in, chemical engineering, classical, consulting engineering, drinking water, sewage treatment plant, process design. So making the bugs work, degrading sewage. After a couple of years working in large multinational consulting firm doing that, poop wasn't really to my taste, if I can use that phrase. But luckily, I was able to pivot into the industrial wastewater side.
Okay.
And the industrial wastewater is primarily anaerobic digestion for high strength waste.
Right.
So my boss at that time, I didn't know this, but he was involved in some of the first farm digesters in Ontario in like the 81, 82 time frame back then. So there were 6 built in Ontario on farm.
Okay.
Now in those times, oil did not go to $200 a barrel.
Yeah.
A lot of painful lessons were learned about H2S and corrosion in engines. Feedstock was not that easy to come by. And after a handful of years, all of those first digesters were shut down. Farmers knocked them down. They found better things to do with their time.
Okay.
But luckily for me, he already had some background and strength and some awareness in the industry. So working in food industry digesters in the early 90s was how I got introduced to anaerobic digesters.
Okay. These are like food processing that has a byproduct stream, or?
Correct. Yeah. So when you boil potatoes, for instance, that kind of white schmutz water you get, just 2,000 gallons per minute of that all day long.
Okay.
And you're not allowed to put that in the river because it will kill the river.
Right.
So you have to treat that to meet compliance.
Okay.
And so that treatment is anaerobic digestion usually, because that's the most economical. So then AD was just because it made money, right? It was an economic driver, not because it was cool. It just made money.
And it made money how? Like it was more than just compliance.
Correct.
Already then.
So it was the cheapest way to achieve compliance over what is happening at a sewage plant, which is all aerobic.
Got it. Okay.
Or use a lot of equipment and use a lot of energy to put air into the water. An anaerobic system does most of that heavy lifting, degrading the potato waste anaerobically. some of the plants would be able to take the biogas that's produced and they would put that back into their boilers to displace geologic gas. And again, that was just one for one displacement of geologic methane with biological methane.
Okay.
And in doing that, it was whatever the price of natural gas was. There was no green credit or anything of that sort at that time. So it made economic sense in some projects, and in some projects, the cost of 800 yards of stainless steel piping was too much, and so they flared it in the early days.
Okay.
Right.
But from a treatment compliance perspective, it was by and large the cheapest way to go.
Absolutely, the cheapest.
Okay.
So that is the mainstay in say most of the food industry. Well, a lot of folks will have anaerobic digestion. So major breweries, vegetable processors, meat processors, anaerobic digestion.
Yeah.
Very common.
And then the liquid byproduct is then going into a sewer system?
That's going either into a sewer system, into a city, or it's going into some sort of polishing, something that looks a little bit more like a conventional sewage treatment plant. And then from there going into a lake or river, some natural discharge environment.
Wow.
Absolutely.
Okay.
Yeah, and so those plants all over the world. So I was working on digesters in Canada, the United States. Managed a big installation digester project in Argentina and South America.
Wow.
Working on projects in Europe. Absolutely, all of those things.
And you're doing this from the perspective of still as a consulting engineer, as a design engineer.
Correct. Right? Yeah. So we're working for the owner, and so the owner developed, because they were super smart. The owner developed this really great way of putting together hybrid projects.
Yeah.
So we would be involved in, say, the process design.
Yeah.
And getting a project to a 20 or 30% design stage. So we would know exactly how many doors and windows in the buildings, how big the pumps were, all the major process equipment. And then we would go to a local design builder who would have a local PE stamp in, some part of the United States, in South America, in France. They would check for, seismic, snow loads, wind loads, local code compliance. And get the thing built.
And would you do the technology selection?
Yeah, so we would work with the owner very closely on technology selection. So typically, we would work with them. We would do the technology evaluation, whether it's different styles of pumps, different styles of mixers, different styles of heaters, and eventually triangulate in on what was going to be the best total cost of ownership for the facility for an owner who wanted to run these things for many decades to come and would have a fleet of more than 40 facilities worldwide. So they had some experience and we had some experience, and then we built plants together and got some more experience. But then eventually, as we sort of honed in, we knew pretty fast what it is we wanted in each respective project.
Got it.
And the owner liked it because the responsibilities were really crystal clear, right? If the pumps didn't pump, or the mixers didn't mix, we knew exactly, it's this supplier or that supplier. If the tanks leaked, it's either the tank supplier or the tank installer. And ultimately, if the bugs didn't bug, then that was my problem. Right.
Yeah.
So that's kind of how that worked from a process perspective.
Okay. So the bulk of your career, kind of after you decide that, municipal waste is not for you, and you get into this industrial space, that's really the bulk of your career.
Yes. Absolutely. And then when I got out of the multinational consulting engineering firms, which would have been just over 12 years ago, and started my own thing and grew into Azura Associates now.
You've been doing this for 12 years now.
I have. Wow. It's been immensely entertaining. The ups and downs. And I thought, well, the bugs are the same everywhere in the world. I don't have a design team. I'm not going to build a big job myself.
Right.
Doing a 50 or 100 sheet job, might be the end of me at this point. But certainly, I think we have things to say and ways we can help owners, get projects built, get them built faster, getting them up and running sooner. And have robust business case, really.
And I think that that last part about the robust business case, I think in our space, whether it's biogas and RNG, whether it's where we come from before, which was cogen. Like, I'm curious your thoughts on this. Like, I think owners often fixate on kind of first cost and even running cost, but the other variable that I think doesn't get enough kind of focus is uptime, right? And that's a broad description, and it means something even more specific in what we're talking about today. But curious about that piece of, hey, you can save some money on how you build it, but you got to, as you mentioned earlier, a 20-30 year life on this asset. And you're going to, in my personal view, you're going to forget about that first cost when you're griping about, low uptime or low output, right? So, I mean, you probably have a much better view of that than I do, but.
One of the things that we do for some owners is we're able to tunnel into their SCADA system, and we're able to look at, kind of on a couple times a week, look at some of the charts, the uptimes, different things on their engines, or we get the Hydro One reports emailed in. And so I was looking at some, and we're looking at facilities that are looking at like 60% of nameplate electrical output. And why is that? Is it because we don't have the feedstock, bugs are unhappy, we got to change the spark plugs on the engines, whether we're doing that more often than we thought or not? Like, what is the issue? Grid trips, lightning strikes, like you name it. The whole myriad of issues with the Ontario FIT contracts, right? When a day of production's lost, like you are never getting that back.
That's right. Yeah.
And so it's really a lost opportunity. With, I think in our staff, like we talk about this, and the one of our gripes is lost opportunity, right? And just unfulfilled potential. Just kind of grates on us a little bit. And so we're seeing these plants, and they're not at nameplate. We have lots of talks with owners, so in different business cases, right? So some owners, they're comfortable, their core business, they're dairy farmers, they've have that as their core business, and they're doing other things. Right? That is their absolute decision to make.
Sure.
And so if this is running at 75% but takes almost no effort, their call.
Right. Fair
versus point. What's the incremental cost to benefit of doing more and getting more.
Yeah. It's asymptotic, but
very much so.
But I think at 75%, you still have a lot of upside before you get to the asymptote. But
yes. So some of the business owners, we're working with, say in the U.S., for instance, they are interested in being multi-state fleet operators.
Okay.
And so they have a completely different view from, I've got my 200, 300, 500 milking head here in Canada. We're looking at some projects south or very south, like 50, 80,000 milking head, like just staggering projects, right? And so completely different mindset. And then the multi-state operators, they're the ones who are looking at it differently. As I said, like this hybrid approach. Okay, we can build one, and then the second one will be better, and the third one will be better still. But by the time we get to number 4, we should be kind of honed in on what equipment works well. What works well in our climate, with our kind of feedstock, with our kind of bedding and XYZ food waste. What suppliers can we count on? Who's got spare parts? When something goes sideways New Year's Eve, who's going to help us and who's going to hang us out to dry, right? And so that's where they are now, is they're looking to build a multi-state asset that will have legs for a lot of years to come. So they're looking at it from a completely different perspective. Absolutely.
Let's, we're recording this on, I think it's the 4th of September. It's the second day back to school. We talked about, our kids are off to different institutions, but all kind of back to school. Let's maybe step back and kind of go back to school on the biology, microbiology kind of process piece here, because, I tried to draw a comparison of power gen and biogas, and there's a lot of similarities in terms of uptime around, mechanical components. But where they start to really differentiate is, in power gen, whether it's natural gas or even wind and solar, the resource that drives the power gen is relatively predictable. But in our world, and particularly in your world, you have this, microbiological process that is providing the fuel for this, whether it's RNG or power gen equipment. But you've got, a variable that doesn't exist in many other types of projects. So,
Right.
So maybe kind of start and just explain to us kind of anaerobic digestion from a very high level, pretend that you're talking to somebody who doesn't know it at all. And you talk about it. I mean, there's kind of different temperature ranges, there's different steps to it. To the extent that without going too deep, and we're both engineers,
Okay.
we'll get probably too deep, but give us kind of an overview, and then we'll pick away at it, just so that everybody understands kind of what we're talking about when we talk about the bugs, or we talk about the biology, the feedstock, all that kind of stuff.
Sure. Thanks. So anaerobic digestion it's a natural biological process. It's been going on in nature for thousands and millions of years. And so it's not particularly new or exciting from that perspective. So it happens in the bottom of lakes and rivers, in the muck of swamps. When a fish poops in the water and it sinks to the bottom of the lake, it breaks down. So there's no oxygen down at the bottom of the lake. So that's what's called the anaerobic environment. There's no oxygen.
Right. The opposite would be aerobic.
Aerobic. Right? So the top is aerobic. That's where the fish like to swim around, and fish are very happy in an aerobic environment. Lots of air in the water for the fish to get the oxygen to breathe.
Yeah.
The anaerobic on the bottom in the mud, that's where that other process without oxygen, the anaerobic digestion, breaks down.
Okay.
And so that whole process is breaking down in nature the material without oxygen. And so this naturally occurring process that happens in the bottom of warm lakes and rivers, or very, very slowly in colder lake environments, or in the ocean. As scientists and engineers, humanity has figured out how to package this up and intensify it and exploit it to get useful energy out of these things now.
Okay.
Much the same way that we'll take fruit. So fruit can fall off the trees, and those windfalls, they can rot and ferment a little bit, which is naturally occurring yeast, and they can actually produce alcohol.
Okay.
And so, like, apples can generates a little bit of apple cider inside an apple.
Right.
And if you ever see some birds walking funny around an apple tree, they have a little bit of alcohol from some of those things. So what humanity is taking advantage of with, say, beer, wine, cider, making yogurt and fermented cheeses, sauerkraut, pickles, all of those natural fermentations that we've been using for food processing also happen in nature for waste disposal. And so we've been, exploiting that for waste management now.
Got it. Okay. Okay.
So it is a multi-step process. There's a lot of different kinds of bacteria or microbes that are involved in this process.
Yeah.
At the heart of it, the engineering version of this is it's a tank with a mixer and a heater. Right? It's not a rocket ship.
Yeah.
In nature, this happens pretty easily, say, in the stomach of cattle and livestock.
Yeah.
The engineering version, tank, mixer, heater, like that is really it. The tank is to hold it all together.
Yeah.
Have some kind of container where we can keep the air out, keep the oxygen out. The mixing, well, the bacteria don't have mouths. So if I've got a steak, right, bacteria can't take a bite out of that steak. Instead, we have to wait for that steak to slowly dissolve.
Okay.
It takes a long time to dissolve a steak. So I think, okay, if I don't have a mouth, how am I going to eat a steak? Well, you could put it in a blender of some kind, make a smoothie, right?
Yeah.
So that kind of pre-chews it. Now it's all little tiny bits.
Okay.
And the other little bits of floating sugars and whatnot in it. Well, if you're bacteria, your only choice is to soak that through your skin.
Okay.
Right? You don't have a mouth, so you have to soak it through your skin.
Right.
And that's why we got to get it really, really small so it can dissolve and soak through the skin or the cell wall of these bacteria to help them break it down.
Okay.
And as part of their natural respiration process, they release carbon dioxide, methane, hydrogen, right? Other gases.
Yeah.
And that's because we've put it into a tank, we're able to then harvest that off the top.
Yeah. Now my recollection is there's kind of like, isn't there like 4 stages, like hydrolysis? Isn't
Yeah.
there?
Depends where you go to school, whether it's 3 or 4.
Okay.
So I follow the American school where we call it 4 stages.
Okay. Yeah.
In fact, and so in our work, we've actually re-envisioned this as more like closer to 6 or 7 stages.
Oh, okay.
Because the classical 3 or 4 stages is an academic version where you start with hydrolysis. We call it hydrolysis, where you start to dissolve, the material starts to dissolve.
Yeah.
And then it starts to ferment and starts to, form, smelly organic acids. So if you smell kind of that rotten potato smell under your sink, that's the smell of organic acids being made.
And that happens in hydrolysis.
And that happens in fermentation. So it starts to dissolve.
Yeah.
And then ferments.
Okay.
Starts to get a little bit smelly. So like sauerkraut, pickles.
Yeah.
Right. Fermented foods, kimchi. That can then become acetic acid, or we'd call vinegar. So we actually make vinegar. So pickling, and then that acetic acid, that vinegar, is ultimately what gets converted into methane. Different bugs do those different steps,
right?
And they each like a little bit different environment, and a little bit different temperature and a little bit different condition for them to work well,
right?
In one big tank, they'll work pretty well together. None of them perfectly, but all of them good enough.
Okay, yeah.
What we've done is on top of that is we said, well, now when food waste comes in, it doesn't start dissolving exactly. Typically, we put it into, say, some kind of a chopper system. So if we've got, where I live, we have green bin waste. So we have a little bucket on the kitchen counter, banana peels, onions, you name it, stuff goes in. When that goes into a digester system, often there's like a shredding step, a chopping step, some way to just make it physically smaller, where it breaks down. Often there are other steps, cleaning steps, where they're, say the plastic bags are getting removed from the waste, or heavy bits of grit that can damage equipment. So sand, glass, bone chips, little bits of bottle caps, things like that can be removed. And then it's only after that happens that we get into this hydrolysis process where the material starts to dissolve, right? And then ferment down the chain.
That's partly why I asked the question. I mean, I was hoping you'd use the term acetogenesis, but but I've been racking my brain trying to remember what the 4 stages are, and that's about as far as I got. But anyways, the other reason I asked was there's kind of a couple different schools of thought as to whether you separate those phases physically or you isn't that right? Like is the industry still talking about that?
Yes. So of the 4 stages, the hydrolysis, acidogenesis, acetogenesis for the acetic acid, and then the actual methane production, methanogenesis process. So of those 4 steps, the hydrolysis is the slowest. So that is rate limiting. So anything we can do to speed up that hydrolysis process opens up the pipeline on the whole system. So that's where folks who are looking at chopping, grinding, shredding at the front end, they've got a pretty good chance of some ROI. If you can look at taking your material from, say, 5 centimeters or 2-inch solids down to a 1/4 inch, it's easier to handle. Your pumps don't plug, your heat exchangers don't plug. But at the same time, there's more surface area for the material to start to dissolve, for different bacteria to get at it and to help the material essentially rot inside the tank. And then all the way down to if you're sub like 1 millimeter size of solids, or even 2-3 millimeters, then you have just a much better chance of a much faster getting to that hydrolysis stage. And then the whole pipeline is faster from there out.
Got it. So we've got this biological process. We've got these bugs without mouths that we want to keep happy. I mean, I would imagine there are some pretty key things we want to watch out for in terms of either kind of design of a system and then operation. Like what are the if there were 5 or 6 kind of hot buttons around process design or process optimization or operation? What are those key areas?
So I would say temperature is our first one, pretty much always. All the bacteria and every living thing has a temperature range that it likes and is happy at and performs well at. And outside of that range, it can be it can be stressed, it can slow down or become dormant or actually injured or killed.
Okay.
Right? So whether it's too hot or too cold,
right,
there's a key temperature range for us. Typically, most digesters operate in what we call a mesophilic temperature range, so medium range, which is about 38 degrees Celsius, 95, 98, 100 degrees Fahrenheit, in that range.
Okay.
And I give a range. Again, the scientists, differ from the engineers a little bit on this. From an engineering practice, if the temperature is stable, it's best, rather than going up and going down.
Yeah, right.
Whereas, for any one particular kind of bacteria will have its own personal favorite temperature spot. But because we're dealing with thousands of different ones, we just need the group of them to be happy.
Right.
And so the group of them likes it to be stable. And whether it's 38 or 39 degrees Celsius, that's not a difference I get too worked up over.
Yeah, got it.
As long as the owner can keep it steady.
Okay. So stable temperature is
stable
number one.
temperature, absolutely number one. The other range is pH. So pH is usually a dependent variable, so you get the pH you get depending on what you put into it and how it feeds.
Gotcha.
So we'll see some farm digesters that will run a pH of, say, like 7.8 to 8.0 range.
Which is slightly basic, right?
Slightly basic, exactly. So 7.0 is neutral. So 7.6, 7.5, 7.4, lots of digesters operate in that range very, very well, depending on the natural balance of how fast we're feeding it, how fast we're making acid, right? So remember that vinegar, that acetic acid. So we're making acid, so there's always some acid in there, and we're always taking some acid away to make methane out of it. So the balance of the acid that's in there is we're making acid, taking acid away, however much acid is there, drives our pH range.
Gotcha. Okay.
On industrial wastewater, we've seen lots of digesters that are pretty happy at a 6.8 range, 6.7.
Okay.
Or even some of them a little bit lower. They naturally operate on quite a bit more acidic capacity.
And does that mean that, deep in the hierarchy of those bugs with mouths, they're different, or are they the same and it's different feedstock? What makes the difference between, slightly basic versus slightly acidic?
Typically, it'll be the feedstock chemistry. So something that has more alkaline material and alkaline reservoir going into the feed. If we're a food processor where we don't have a lot of physical chunks of solids going in, so we have a lot of water from, say, washing the floors, washing equipment, there's not a lot of what we call alkalinity in that water to begin with. Okay. If we're coming from an agricultural side or a food waste where there may be a fair bit of alkalinity, some calcium, magnesium, all those good minerals you and I and everybody needs to grow and be healthy. There's a lot of those minerals in the manure and in the feed. So those minerals end up in the digester and help keep it nice and neutrally.
So the bacteria has some flexibility. They can live at slightly basic, slightly acidic. It's a function of the feedstock. Yeah.
Exactly. And from the thousands of bacteria that go in, enough live at the different pHs that they're able to function as an overall system. Right? So temperature and pH, like I said, mixing. So just as they don't have mouths, they don't have legs either. Right. So when you and I, when we get hungry, we know where the buffet is. We get to walk over there. Right. Right. Bacteria can't do that, so we have to bring the food to them. And at the same time, we have to take the waste away. Right. So having a good mixing environment is always pretty important that way as well. Okay. Also a balance of feed. So when we are looking at a digester, we always start with macronutrients. Okay. So things like if you're thinking of buying fertilizer at the home store to go on the garden, so it's potassium, nitrogen, phosphorus, right? Those are pretty key macronutrients where a digester might need hundreds of pounds per day of phosphorus to keep all the bacteria going. Okay. There can be minerals as well, so things like iron or sulfur, things of that sort, that might need tens of pounds, 20, 50 pounds per day, 20, 30 kilos per day to keep the biology happy. And then all the way down to, say, trace metals, where just again, same as bacteria. So you and I need vitamin B12. Right. One of the things in vitamin B12 is cobalt. Okay. And so cobalt is a key metal that is required to make the enzyme that helps the methane bacteria or the archaea help those methane bugs make methane. They need cobalt to do that. And so that we get cobalt from vitamin B.
Yeah.
You know, they can get it from, again, whatever that feed is in that the animals are getting, or in the other waste that's coming in, say, again, banana peels from your kitchen.
Got it. Okay.
One of the things we found is nickel is often thought of as a fairly critical trace metal that a lot of digesters don't get enough of.
Okay. Okay.
And so what we find is for the folks who are taking, say, food waste from a factory, they almost never have nickel problems.
Okay.
Right? These stainless steel pipes.
Of course. Right. Yes.
Right? In most food factories, in the stainless steel equipment, there's enough nickel that is shed off those pipes, whether they have some acidic water in the pipe, they get just enough nickel dissolves in that those facilities, a lot of them never have trouble with nickel problems, being low in nickel. Whereas some other type of industry might have low nickel and might need to supplement, but that's you know, less common. So very industry specific.
And so you're looking, when you talk about kind of the right feed mix, you're looking at a combination of what are you feeding into the digester to get energy from, and then you're like most Canadians do in the winter, you're supplementing vitamin D as an example, right?
Sure.
You know, you as you know, the service provider are suggesting they supplement what they don't get naturally from the feedstock. Is that kind of how you see it from a design and operation perspective?
Typically, yes. So on the farm digesters, most of them do not require supplementation.
Okay.
The farm digesters that are strictly manure, most do not. The ones who are co-digesting with some other off-farm material, depends.
Okay.
And so I would say probably maybe a quarter of them would benefit from supplementation, but again, most do not.
Okay.
And that's because there's enough nutrition in the manure or in the spilt feed or the bedding or whatever that those nutritional needs are met that way anyway.
Got it.
If what we're getting for off-farm food is just sugar, we're getting spent soda. You know, we're getting you know, I don't know, Coca-Cola syrup or whatever from some branded syrups and juices and water and spent beer or spilt beer that comes back in the bottom of kegs. You know, there's really no nutrition in that. It's just sugar. So there's not nitrogen, phosphorus, all of those things. So it's like, you know, like my mom always said, right? Eventually you got to eat a broccoli now and again to get the rest of your nutrition covered off. Right. And so, if a digester's just not feeding manure, but is just feeding melted ice cream, it's absolutely going to run into problems.
Got it. Okay. And are you looking at this, you know, if and when, this assessment of if and when to supplement, is that something that's done at the beginning? Are you doing that on an ongoing basis? Like, how does that typically happen?
Both.
Okay.
Both. So when the project developer or the owner is looking at their feedstock blend, we and others, there's enough experience in the industry, I think, to have a pretty good handle on what might be required. But it's not until the feedstock contracts actually come to fruition and the material really does show up on a truck that you know for sure what you're actually going to get, and what you're going to get this month, what you're going to get next quarter, what you're going to get you know, after the 4th of July, right, and the various holiday periods. And it's only over the course of the first probably 2 years that you'll figure out what would be an average input.
Got it.
You know, in that stage. And then to source those, so there's specialty providers who will source nickel and cobalt and, you know, different things. Some folks self-manage. Right? They just are able to, you know, take some samples and send it to the lab, ask how much whatever nickel, cobalt, zinc is in it. And they can go to the co-op. So they can go to the agricultural feed store. So just as there's an agricultural premix for livestock, you can get a mix for your dairy cattle that will have zinc and selenium and, you know, XYZ trace metals. You say, great, I want a bag of this, and I'm just going to throw it in my digester instead, right?
Really?
And you can get most things that way. It's, again, there are specialty providers that do that. We help some people self-manage it or different things, and they can just do it themselves, right? There's a lot of ways. Just kind of depends on like a lot of things, if you want to shovel your own driveway or if you want to hire someone else to do it. But it's again, it's not a rocket ship.
Yeah. And are you? Is there a rhythm of taking samples out of the digester and testing that, and maybe kind of changing the supplementation based on that?
Yeah. Yes, with an asterisk.
Oh, okay.
And so that's the financial piece of it. Is so as a pure consultancy, so we've done studies for these food processors and helping them put together trace metal blends, and they can source that from their local animal feed store, right? That's a fairly expensive piece of science to do.
Okay.
Whereas, same for you and I, we can have customized medicine.
Right.
We can have fine-tuned MRIs and help us balance our nutrition perfectly. But the reality is, like that might cost $5,000, whereas, for $40, you can just take your Flintstone multivitamin once a day and eat all the French fries you want. Don't worry about it, right? So it gets you enough forgiveness, the low cost catch-all. So there are both schools of thought for sure. And I think it's really one of scale.
Okay.
Typically, the cost of the mineral itself is not the expensive piece.
Oh, okay.
Right? The expensive piece is doing the sampling, doing the lab work, doing the analysis and the calculations. How much do I need?
Yeah.
And then I'm going to have a staff member who's going to be measuring out, 3.5 teaspoons of this powder.
Right.
4 times a week into my thing. And so that whole process, right? It takes hours to do it for a little bit of thing.
Got it.
Whereas if I have a pre-blend, maybe it's got too much of some things, but it covers all my all my sins. I'm forgiven, and I just put this in, and
got it. Okay.
And we can put in the ice cream and the beer and the soda, and just make lots of gas.
Right.
So definitely, there's a few ways to do that.
You mentioned the scale. Is there? We've been talking through these kind of critical success factors. Is there? Is there a success factor around kind of the size of the digester?
It is. I hate to say it, but I think there is.
Yeah.
Right? Because, so better than me on the RNG upgrading and the injection side of that, just the cost we're talking about of dealing with the gas utility and the compressor station and putting it into the grid, right? That's a fairly expensive undertaking. Like, off the top of your head, what would you say in terms of like that piece of the puzzle?
Yeah, it's significant. Yeah. No, my question more was around like hydraulic retention time.
Oh, yes.
And you and I can go across town to the Mandarin and gorge out, and we're going to feel it, right? We're going to eat too much for our metabolism. In terms of you have a finite size digester, or maybe you're in the design phase and you got options, but how does you can't just there's a limit to how much you can shove through, I guess is really where I was going.
There is, I think. So there's some really interesting for me, I'll say, some scientific publications around this, that a very long retention time has enough what we call internal nutrient cycling. So this bacteria dies, its body breaks down, it releases the nickel back into the fluid, and his neighbors get to eat it.
Interesting.
And so if we're at 75, 80, 90 days retention time, trace metals pretty much never help, right?
Okay.
Because the biology is in there so long, they live, they die, they break down, their neighbors get to eat them, and there's enough internal nutrient cycling. It's where we want to optimize, right? So that's where if we want to get down to, say, 30 days, 25, 20, now we're starting to be performance oriented.
Yeah.
And so, if anybody's got a digester at 75 days, we could probably double your throughput without even trying, right? Like that's easy.
Yeah.
But at 30 days, depending on how complex your feed is, again, just like us, and if you ever look at your own human nutrition, we eat sugar and fast carbs, like sugars and rice and white bread and fast carbs. We're able to break those down pretty fast. Fats and meats and proteins are slower to break down. So when we're running at, say, 30 days, that's still a pretty good long time. 25 days, 20 days, getting down to 15 days. Now we're really starting to shave and to optimize the process. So we need as much pre-chewing, that hydrolysis part, right? We need to physically make the stuff small enough the bugs can get at it quickly. We need to do whatever we can to improve how it's working on that front slow hydrolysis process.
Yeah.
And then we need to make sure that the bugs are never slowed because they don't have quite the right nutrition.
Right.
So like I said, so you know, you and I do pretty well on cheeseburgers and fries, but we're not in the Olympics. Or sorry, I'm not in the Olympics anytime soon.
Right.
And so presumably, if for that kind of peak athletic output, I'd actually have to pay attention to what I ate.
That's a good comparison.
Right.
I like that.
And
Yeah.
so,
okay.
Yeah.
And then by contrast, you mentioned industrial digesters. My limited exposure is many of them operate, you've been talking about 30, 25, 20 days. Many of them operate where they're measuring retention time in hours.
Absolutely.
What's the difference there?
So this is a really excellent point to clear up. How fast or how slow your material breaks down depends on the material itself in the feedstock. It has nothing to do with how clever your technology provider is or what the shape of the tank is.
Got it.
It's 100% based on how complex the chemistry is of the feed.
Gotcha.
So a complex feed that has a lot of cellulosic material, straw, corn stover, silage, right? Because that material is chemically complex, you would want your 75, 80, 90 days retention time. A sugar factory, that's mostly just sugar in the wastewater, might be 4 hours.
Right, okay.
Right?
Gotcha.
And that's because the sugar is super simple as a molecule. It breaks down really, really fast.
Yeah.
So 4 hours. It's not because the vendor of the 4-hour system has any magical powers or secret knowledge. It's just that they're dealing with sugar.
Yeah.
And so the intermediate stuff, so the ice cream manufacturers, you got sugar and fat, they've got a certain typical retention time that is typical for that industry.
Got it.
For industries that have, say, higher solids, the solids, again, we're back to the mouth thing, because they have solids, they are slow for those solids to dissolve. And once they dissolve, then it breaks down pretty quickly.
Gotcha. Okay.
Right. So for example, for meat processing, you can do a little experiment at home tonight. Maybe not. Take a steak, like put a piece of meat in a glass of water and leave it on the kitchen counter for like 2 months. 3 months. Right. And you're looking at how fast that piece of meat just dissolve in a glass of water. Right. It takes a long, long time. Right. Whereas if you take a chunk of apple and you throw that into a glass of water, right, it'll break down in a couple days pretty fast.
Okay. Wow.
Right?
I love
it's that distinction, similar to some soda, throw it in a glass of water, it's already dissolved. Right. And so that's the one where it can go in hours versus days versus weeks.
Okay, kids, that's your homework for this week. Steak versus apple in a glass of water. Tell mom and dad we approved that.
We approve. Let us know how long it takes to break down.
Right into the show. Sure.
Absolutely.
Okay, so we've got these critical success factors around temperature, pH, mixing. We've got the diet and these trace elements and macronutrient, macro and micronutrients, and then we've got kind of retention time, which is kind of tied into the feedstock.
Absolutely.
That's kind of the gold standard and where we want to aim towards.
Yes.
I would imagine in your illustrious career, you've seen some examples of where that has gone sideways. To the extent that you can share, do you have some stories you can share, Dave?
I do. I'm just gonna have to edit this in my brain here for a second.
We can always, Mark can always edit it out. After
All right.
the fact.
Thank you, Mark. Don't get me in trouble here. When I got out of the big consulting game, right, I was trying to figure out how to help these projects survive. Because like ultimately, waste energy, like this is the only carbon negative fuel we have. Right. Yeah. And so it's important for these to survive. So one of those early CBA conferences, tremendously grateful for the folks there for putting those on, ran into a farmer who had a digester and Dave is making no gas. So I just bulldoze this thing and plant corn. I'll make more money on it. And this thing's just a headache. So hang on, let me come out there and have a look at it. I'll see what I can do.
Yeah.
And so sure enough, I went out. It was cold. It was acidic, right? The pH had gone down a little bit too low.
Okay.
It was not making any gas. I said, well, don't worry. I'm sure we can bring this back. And in a couple months, it was back up to temperature. The pH was back in spec. It was making gas again. It was making gas so we could run his engine and make some more heat. And so that all worked well. And then over the course of about 2 years, sort of coaching him along the operations and the different feedstocks. Should I take this feed? Should I take this? I got a call. Should I take this other nonsense? We were able to coach him through all of that process. So at the end of probably about a 2-year span, he decided to double down and get another digester.
Okay. Wow.
So that was interesting from us from that perspective that he was thinking of getting rid of them and he ended up getting another.
That's
which
amazing.
It helps. It helps diversify the farm income first off.
Totally.
Helps get waste out of landfill, which is kind of one of the key things we want to be about, and helps the environment and the community. So we love that piece. And so that was just in terms of projects gone wrong or could have gone wrong.
Yeah.
I think it was because being relatively new to the industry, not perhaps understanding some of those critical success factors. The temperature got away from a little bit.
Right.
The gas production dropped a little bit, so the engine dropped a little bit.
Yeah.
Not quite enough heat going into winter. Okay, now we're at 32 degrees Celsius, not 38. And we start to build up a little bit of acid because we're not breaking down the acid as fast as we used to be. So the pH drops, 6.7, 6.6. We're not making enough gas, and now we're at like 27 degrees Celsius, right? And so those things all feed back on each other and spiral. Yeah. So in the industrial wastewater world, we call that the digester death spiral. So it's a pretty well-known phenomenon that happens. Okay. When you hit a low enough pH, the anaerobic bacteria, the methane-produced bacteria drop off entirely. Yeah, right? Okay. Another project, it's a marquee project I can only speak about kind of obliquely, is that there was some piece about how they were handling the digestate and what they were doing with that. Okay. And some of the things that weren't really appreciated at the early, like the FEL 0, the early pre-design stages of what do we do with digestate? If we put into some kind of dewatering machine and we get some solids out and we get some liquid out, what do we do with that? But if our feedstock's a little bit dry, well, that's great. I got all this water here. I can just put this back in the front of my digester. And I'm sure you've seen this too. So we're not just bringing back water, right? So that's where, as far as say your mechanical designers, if I can move it with a pump, it's all water, right? And whereas the rest was like, well, it's water. It's got salt. It's got ammonia. It's got X, Y, Z stuff in it. And so that's where if we bring back a bunch of ammonia, nitrogen, and we mix it up with a bunch more digestate, that's fine. But the next time through, we got double the amount of nitrogen in the water this time. Yeah. And we're going to bring that water back around again, and we're going to put it through a third time. Yeah. And then eventually we build up so much, could be sodium, potassium, so salt, could be ammonia. We build up something that harms the bacteria to the point where they got a real serious problem on their hands. And
that reminds me of the project we're kind of developing together right now, where we've contemplated ammonia stripping, I think, to the extent that I understand it, for that very reason. We may have to recycle some stuff, or we may, and so we're cognizant of that early and trying to bring that out ahead of time, right? So,
exactly. So that's the key piece, right? Yeah. Because we've got a pretty good handle, or like again, the scientific community has a pretty good handle on salt. So like a freshwater fish isn't going to survive in the ocean. Right. An ocean fish isn't going to survive, in a freshwater bathtub. Right. Similarly, how saline the water is matters. Right. Okay. And so that's where things like commercial ethanol production, so like fuel ethanol production, very, very high in salt. Okay. Right. So we've seen it that in general, right, those industries look like those should be great opportunities. Yeah. But they are also very high in salt. So everyone who's familiar with digesters knows to watch for salt. And so it's not a unsolvable problem, but it is a problem. It is an attention point that you need to consider at your early design stage. As you're still moving boxes around on the whiteboard, think about your salt, think about your ammonia.
Yeah.
Right. And if you got those two things cracked, you're probably pretty good shape.
Got it.
Overall.
Are there any other, we've talked about some horror stories, talked about some, kind of the key success factors. Are there any other kind of lessons learned that, in your brief career that you let's imagine that somebody's listening to this who's maybe in a development role on the early stages, whether they're an industrial waste producer or somebody in the ag community. Like, are there some other lessons learned that come to mind for you?
So the way that we've seen projects stalled, and tragically in the last 12 months even, we're seeing projects like major projects being mothballed.
Okay.
And
projects that were operating?
Yes.
Really?
Operating, making gas.
You're kidding.
Running afoul of, a variety of situations.
Yeah, yeah.
And so things like, first of all, feedstock, right? It's very hard to get a long-term feedstock contract.
Yes.
And so if you think we're in the waste business versus the energy business, that's the first kind of mindset. So the folks I think who are coming at this from the energy business mindset,
yes,
I think they might be in for a bit of an awakening.
Yeah, yeah.
As people start to talk about like a 20-year waste contract, like those don't exist in the waste industry.
Right, right.
And so if you want a 20-year contract, because your investors expect a 20-year contract, you're probably going to get that if you sign up for a really, really sweet deal. You give them a bargain,
yeah,
and in which case, how does your project pencil?
Right.
Okay. So feedstock and long-term feedstock supply is a real challenge to be reckoned with. Then conversely, digestate, being able to get rid of it on the back end.
Yeah.
And so that's the same thing. All of the farmers I've talked to, nobody is willing to sign a 20-year contract for putting your slop on my land, right? Because the agricultural community takes stewardship to a different level
100%.
Than a lot of people in most industries. Like if we're talking to somebody who's 4, 5, or 6 generations on a particular farm, it's not my land. It's not even my land for my kids or my grandkids. It's family land. It's a multi-generational asset. And I don't want to be the one who puts chopped up rubber gloves from local factory out there.
Yeah.
So that kind of thing where investors from across town or out of the country or overseas or wherever, they have a different way of dealing than the local community, both on feedstock supply as well as on digestate disposal and land application. Right. So those are the real key things that the sewage world, I'll say they conquered the basics of digestion in the 70s and 1980s.
Okay.
Digesting this kind of stuff. Okay, so that's the newer bit.
Right.
How do we deal with feedstock? How do we deal with digestate? Those are the bits that are still people are learning painful lessons today. And then the third thing I think is time. Right. So the timing to get approvals, to get grid connections, is something that I think early on some people are unaware of. Just how long some of these processes can take. On a national scale or a grid scale, RNG today is not that great of a portion, right? In terms of moving the needle on a national level, it's not that big. Frankly, it's a critical and important waste management tool. Like even where we are in Ontario, the landfills, saw one report, going to be full in 10 years, less than 10 years.
I believe it.
And we are still today, we're trucking waste into the United States. So if it takes more than 10 years to get a permit for a landfill, and we got less than 10 years left, we are today already in a pickle. And so managing our own materials is something I think we need to
that's good.
taken. Digestives can definitely help with that.
Right. They're not the only solution.
But they're not, they're not the only solution.
They can be a big part of it. Yeah.
Absolutely. And help push off the timeline on existing landfill space while we sort out some longer term solutions.
Yeah, I love it.
Yeah.
So as we land the plane here, let's go closer to home in terms of 12 years ago, you start out on your own.
Mm-hmm.
You know, take the leap of faith into being your own boss, the good and bad. But talk to me now about 12 years later, Azura Associates.
Yeah.
What are you guys doing? Who are you? That kind of stuff.
So there's 5 permanent full-time staff as core, everyone process engineer, chemical engineering, environmental engineering background. And we are supported. We have a team of 4 like part-time independent contractors who support us on all things.
Yeah, yeah.
From financing, marketing, bookkeeping, the whole suite of it. Our plan, I guess, like everyone, is global domination.
Right.
Yeah, right.
Yeah,
absolutely.
Yeah.
But through the miracle of the internet.
Yes.
We have been just astounded at the opportunities that come in the door.
Okay. Yeah.
So we have investors from South Africa wanting us to help them look at projects in California, and they end up, at our doorstep in Waterloo in the backwater of Canada.
Yeah.
We have investors from Geneva with finance people out of like Budapest and the Middle East, tech teams working out of somewhere in Pakistan. Like I'm not actually sure exactly where they are. Looking at projects in Latin America.
Okay.
The world has shrunk tremendously. We get inquiries from like Hong Kong, Southeast Asia. It is just mind-blowing, kind of some of the opportunities.
And you're providing advisory, consulting services to them as they evaluate project investment decisions? Is that most of your work, or how does your work kind of flesh out?
That's a super good question. I have to think about it today. So right now today, we are mostly working with owners who are looking at either just managing their day-to-day operations, or most of them are actually looking at expanding operations.
Okay.
And we work with developers who are looking at new projects, so helping them assess feedstock, doing independent risk analysis, due diligence, before the EPCs or the technology vendors get too close to it, like a FEL 0, more of a design basis, early stage. And then once in a while, thankfully not too often, we get involved in some of these projects gone wrong, whether it's like independent review, arm's length review of something, if the parties are all speaking to each other still. Root cause analysis workshops, those kinds of things, where something's gone wrong and everyone just wants to fix it.
Right.
Involved with those. And sometimes, though, if a ruckus should break out, then we're going to be like we're going to go to alternate dispute resolution, mediation, arbitration,
expert witness kind of stuff.
That kind of stuff. Yeah.
Wow.
Putting that together. But thankfully, not very much of that.
Yeah.
Most of the projects should be successful.
Yeah.
And can be successful.
Yeah.
We just got to get them there.
Right.
That's it.
Right. Yeah. Yeah, it's almost, without, I don't think this is your marketing plan, but it's almost like people will hire you at the beginning or at the end. And it's probably better for everybody if they bring you in at the beginning.
The beginning is the best. Like we would like it most at the front end, because certainly having crawled around the bones of, enough projects, it's like, man, like all of these lessons, these are easily solvable things.
That's right.
This thing that's $25 million on the back end, this was really a $20,000 problem at the front end. Like really, we could have solved this.
Yeah, when it's on the whiteboard, it's cheap and easy to fix, right?
Absolutely. Absolutely. That's the point. But as you said though, first cost, right?
Yeah,
versus
that's right.
lifetime cost.
Yeah, there's always that tension.
And so the owners who are new to it may be putting some of their money in the may reprioritize or proportion their costs differently, maybe how you and I would.
Right.
Because we're conservative engineers, we want everything to last 1 million years. Okay, so that's not going to happen.
Right.
But where as you said, that creative tension, where that lands is, all right, we know that these brands of pumps work for us, and if they don't work, I can get spare parts in 24 hours.
Right.
Okay, so the multi-site operators are the ones who are really learning those lessons. And if in this jurisdiction, there's a lot of plastics because they accept diapers into their green bin program, whereas this other jurisdiction does not. We still get a few diapers, but not very many.
Right.
Those kinds of things. It's those real niche lessons that they're learning still.
Yeah.
Absolutely. But likely much more fun on the front end. Well, dealing with plant ops and the day-to-day stuff, that's where some of these lessons come from. Operators are immensely entertaining to work with. They have a very clear speaking way of seeing the world, and they'll take no nonsense. So we appreciate that very much.
For sure. Good. So if listeners want to get a hold of you, Dave, what's the best way to do that? Is there a website?
Yes, it's azuraassociates.com. So Azura, another A, SSOCIATES.com. Azura Associates. Okay. Another time I would make a much shorter URL, domain name. Didn't know that. Anyway, AzuraAssociates.com. There's a web form there for urgent matters. So the web form, actually, it comes to my cell phone. Okay. So, there's a pretty good chance. So
I'll play a prank on you in the middle of the weekend.
Urgent, critical matters. The web form does get looked at pretty much all the time.
Yeah. Awesome. Well, Dave, this has been great. I mean, you and I have had the chance to chat on many occasions, but never kind of this deep. And this has been great.
Thank you.
So appreciate you. I know, for us, time is valuable, and I know you've got a lot on your plate. So appreciate you coming all the way down here and doing this in person. And, as I said to you at the beginning, like our goal with the podcast is really to bring kind of stories and experience and knowledge to owners to really, make sure their projects are as successful as they can be, right? And
absolutely.
So I think you've brought, a lot of that today. So really appreciate you coming down.
Well, thank you for that. Really appreciate the time as well for yourself and the whole team here at CM. You guys are doing some pretty cool work, doing some interesting projects. And I think there's room in the space for more information and more knowledge to get out to the people. So we're very happy to be part of that.
And you guys do great work on social and all the platforms, and love listening. And you got, we didn't have, if we had more time, we'd let you kind of brag on each member of your team. I've had a chance to meet all of them and thoroughly impressed. And this has been great. And to our listeners, thanks for tuning in. Another Energy Radio episode, really getting into the details and the bug dust, literally. So until next time, let's be safe and make our projects as successful as they can be. Thanks.